Well, welcome back. We are now working in section 6.2 and continuing on with the idea of congruence, modulo I and ideal, and we're going to talk about quotient rings and going back and looking at homomorphisms. So let's start with Theorem 6.8 says this: let I be an ideal in a ring R if A plus I is equal to B plus I, and C plus I is equal to D plus I. These are called the cosets for A, B, C, and D elements of your ring R. So if the A plus I coset is equal to the B plus I coset, and the C plus I coset is equal to the D plus I coset, then A plus C coset plus I is equal to B plus D plus I as a coset, and A times C plus I coset is equal to B times D plus I as a coset. All right, so what is this big theorem really telling me here? From our basic idea of cosets, and now we had the congruence, we can add the congruence classes modulo I, but remember now we're using the congruence class notation of A plus I as cosets. We can add them and we can multiply them. So we define this accordingly. Definition: let I be an ideal of ring R. Then the set R mod I, written properly, R modulo I, is the set of all cosets A and B elements of R with A plus I and B plus I elements of R mod I. These are the cosets. Elements A and B are in R, but the cosets are A plus I and B plus I. This is how you write the elements. Are in the R mod I, such that 1. This is how you add them. A plus I plus the coset B plus I. You can rewrite that as just add the two elements, A plus B, and denote it's a coset, plus I. And to multiply A plus I times the coset B plus I, to multiply two cosets, you just multiply the elements, A times B, and you just stick a big old plus I on there to let them know that it's a coset. But more than that, the R mod I is called a quotient ring. And yes, it's going to be a ring under the defined addition and multiplication. So to have a ring, you got to define a set, and you got to define a way of how to add it. That's what we're doing here, thanks to Theorem 6.8, and how to multiply it, again, thanks to Theorem 6.8. This is called a quotient ring. We can create more rings out of this stuff. But here's the big deal. Remember our definition of an ideal. It's a subring with the extra property that if R is an element of R and A is an element of I, then A times R is an I and R times A is an I. It's a little bit stronger than being just a subring. It's a subring that all you need is one element multiplied by any other element inside the ring, puts you back inside the set. But when you have ideals grouped together, they create quotient rings. When you mod out by an ideal, you get a quotient ring. When you mod out by a subring, you get a nice little set of elements, but they do not create rings out of it. You have to have an ideal to be able to mod out by, and the structure of ideals to create quotient rings. So that's always the goal. How do I create more rings? You create more rings, in this case, by identifying an ideal inside of a ring and then looking at the modulo according to that modulo I and creating quotient rings. R modulo I is called the quotient ring. Theorem 6.9 says this: let I be an ideal of a ring R. Then, number 1, R mod I is a ring with addition and multiplication defined, as we defined before. A plus I coset plus B plus I coset is equal to A plus B plus I, it's a coset, and the coset's A plus I times B plus I, that's equal to A times B plus I as a coset. Now more properties, here's this. If R happens to be a commutative ring, if it commutes, then R mod I is going to be a commutative ring. So there's that structure that holds over depending on what kind of ring the ideal came from. So if you have a commutative ring, then R mod I, the quotient ring, will also be a commutative ring. And if R has an identity, it's a ring with identity, then R mod I will also be a ring with identity. And that identity element, we're talking about the multiplicative identity element, would be the identity element in R, which we call 1 with a subscript R. But to make him a coset, we just put plus I. And that becomes the identity element in the quotient ring, R mod I. Now again, as I mentioned before, R mod I is called a quotient ring. But when you get into the higher level math, the senior and graduate level math classes and stuff, they may also call the quotient ring something called a factor ring. Don't freak out, that's just a different textbook calling it something else, but they're the same thing. Quotient rings and factor rings are exactly the same thing. So, when you study quotient rings, then you get to graduate school, and they're all of a sudden they're talking about them being called factor rings. It's the same thing. Somebody just changed the name of it. So I'm trying to tell you now to prepare you for senior level classes and the like. They're the same thing. Quotient ring, factor ring, same thing. So an example here. Let's take a look at Z12. Z12 is a ring. We've played with him before. I'm trying to give you something that we know. And I'm going to let I be equal to, and you've seen this before, the multiples of 4. So I wrote I as that fancy set notation. So in Z12, remember you get elements 0 through 11. So these are equivalence classes. So I is equal to the equivalence class 4 times x, such that x is an element of Z12. It's all the multiples of the 4 equivalence class in Z12. I've played with him before. Now, this guy, because we played with him before, is an ideal. Let that be an ideal in Z12. Let's take a look at Z12 mod I. Now remember, I are all the multiples of 4 out of Z12. Now, out of Z12, I is the multiples of 4, 0, plus or minus 4, plus or minus 8, plus or minus 12, plus or minus 16, ... This would be equal to, in the concept of Z12, would be the equivalence classes 0, 4, 8, and then another 4 would be back to 12, but 12 in Z12 is actually back to 0, so it's 0, 4, and 8. The multiples of 4 in the Z12 equivalence class. So this is the idea of, this is pretty much in just the world of integers. This is the world of Z mod 12, just the equivalence class 0, 4, and 8. Because you add another 4 to 8, you get 12, but 12 in Z12 is back to 0. That's how the zeros element shows up there. So what will the cosets look like in this particular set here? What are my cosets going to look like? Well, here we go. To be the cosets of Z12 mod I, cosets look like A plus I, where A is an element of Z12. So I'm going to kind of write these guys out, and let's take a look at them and catch a pattern. So here we go. So this would be start out with the first element in Z12, I would call it 0, so you're going to call it 0 plus I. So 0 plus I would be pretty much all the elements of I, which would be the 0, 4, 8. These are the multiples of 4. This is actually what 0 plus I is I, so this is just I. The next one is going to be 1 plus I. 1 plus I, you're going to add 1 to each one of these elements. So that would be the equivalence classes of 1, 5, and 9. Okay? I'm just kind of breaking them up, but these will be my cosets. This is what we're talking about, but this is what they represent. The next one would be obviously 2 plus I. 2 plus I would be, you're adding 2 to I, that would be 2. Adding 2 to 4 would give you 6. Adding 2 to 8, you get 10. The next one is going to be 3 plus I, and so I'm going to add 3 to each element in I, which are the elements 0, 4, 8, and I'm going to get 3, 7, and 11. The next one coming over here would be 4 plus I, and then 5 plus I, and then 6 plus I. Let's go ahead and write them all down. And then 7 plus I, and then while we're at it, 8 plus I, 9 plus I, 10 plus I, and 11 plus I. And finally done. Okay, because in Z12 there are 12 elements, 0 through 11. All we're doing is putting plus I on them. But let's take a look at what these guys look like. 4 plus I, we'd be adding 4 to each one of these elements. 0 plus 4 is 4. 4 plus 4 is 8. And 8 plus 4 is 12, but 12 is back to 0 again. 5 plus I would be adding 5 to 0, which is 5. You're always in your own equivalence class. 9. And 9 plus, 5 plus 9, 5 plus 8, adding at 8 would be 11. Excuse me, 5 plus 8 is actually 13. I can do actually math. And 13 is equivalent to 1. Six plus I, that would be the set 6, plus 0, 6 plus 4 is 10, and 6 plus 8 is 14, and Z12, that would be back to 2. Read my handwriting, it's a 10 there, okay? 7 plus 0 is 7, you're always in your own equivalence class there. 7 plus 4 is 11. And 7 plus 8 is 15, but 15 in Z12 is actually back to 3. And I want you to notice that you're getting the exact same elements again. They just rearranged order, but order doesn't matter. And I could keep on going, I'm going to get the exact same elements again. You add 8 to a set inside of 8, you get the same set again. Watch it. 0 plus 8 is 8. 8 plus 4 is 12, but in Z12 that is 0. And 8 plus 8 is 16, and 16 in Z12 is actually 4. So what a surprise, you get the same elements back again. And so this one would end up being 9 plus 0 is 9. 9 plus 4 is 13. 13 is equivalent to 1. And 9 plus 8 is 17, and Z12 you end up getting back to 5. And again, you get the same elements again. And of course, the last two, again, you're catching the pattern here that gets to the same. So 10 plus, this will be 10. 10 plus 0 is 10. You're always in your own equivalence class. 10 plus 4 is 14, and Z12, that's 2. And 10 plus 8 is 18, and Z12, that is 6. And last but not least, 11 plus 0 is 11. 11 plus 4 is 15, and Z12, that's 3. And 11 plus 8 is 19, and Z12, that's 7. And notice you end up getting the exact same equivalence classes. So my point is, once you get past 3, once you go to 4, 4 plus I, but 4 was inside my set. So there's no reason to write it again, and no reason to write it again. So to answer the $64 question, what cosets make up Z12 mod I? They are going to actually be the cosets 0 plus I, 1 plus I, 2 plus I, and 3 plus I. That is what makes up coset. Because 4, the next one would be 4 plus I, but 4 is inside of this I set I here. And when you get back, you say when you add 4, 2 back elements back inside of 4, all you're going to get is I rearranged again, and 0 plus I is I itself. So you begin to duplicate after that. So there are actually just 4 elements in Z12 mod I, where I are the multiples of the equivalence class 4. So what are the cosets of Z12 mod I? Let's talk about this for a second. Well, again, I was the set of equivalence class 4 times x, such that x was an element of Z12, and we just discovered that the cosets are 0 plus I, 1 plus I, 2 plus I, and the last one was 3 plus I. So the question is going to be, what kind of ring is this guy going to be? Knowing that this is now my set, it is going to be a ring. We will show you it's a ring by doing the famous addition and multiplication table of this particular set. So I'm going to put up here my elements: 0 plus I, 1 plus I, 2 plus I, and 3 plus I. And over here, you've got 0 plus I, 1 plus I, 2 plus I, and 3 plus I, creating my little table to do the addition on. And here we go, let's add. Remember how we define to add cosets. You add the elements and put a plus I, but catch a pattern. You can only have 0 plus I, 1 plus I, 2 plus I, and 3 plus I. So 0 plus I plus 0 plus I is 0 plus I. 0 plus I plus 1 plus I is 1 plus I. 0 plus I plus 2 plus I, 0 plus 2 is 2 plus I. And 0 plus I plus 3 plus I is 3 plus I. 1 plus I plus 0 plus I is 1 plus I. 1 plus I plus 1 plus I obviously would be 2 plus I. You add the cosets and then put a plus I. You add the congruence classes and Z12 and then put a plus I to make it a coset. So 1 plus I plus 2 plus I is 3 plus I. 1 plus I plus 3 plus I is 4 plus I. But 4 plus I, 4 is actually the same thing as going to be 0 plus I as you boomerang yourself back. So this would be 0 plus I. And 2 plus I plus 0 plus I is 2 plus I. 2 plus I plus 1 plus I would be 3 plus I. 2 plus I plus 2 plus I is 4 plus I, but 4 is equivalent to 0 in my set as we boomerang back. So that would be 0 plus I. And 2 plus I plus 3 plus I is 1 plus I. Usually it's 5 plus I, but again, 5 is not my set, so 5 would be equivalent to 1 as you go through and do your remainder through and continue to catch the pattern. And last but not least, what is 3 plus I times 0 plus I? 3 plus I plus 0 plus I is going to be 3 plus I. 3 plus I plus 1 plus I is 4 plus I, but 4 is equivalent to 0 plus I. So 3 plus I plus 2 plus I would be 1 plus I. And last but not least, 3 plus I plus 3 plus I is 2 plus I. Visually 6, but 6 is equivalent to 2 in my sets as they boomerang down. This is a finite set of elements. Now, the multiplication table is a little bit more interesting because it's from the multiplication table that we can actually tell what kind of ring it is. When I talk about rings, let's see how many we got. We got ring, basic ring. You got a commutative ring. You got a ring with identity. You got a commutative ring with identity. Then, after a commutative ring with identity, you got the choice of integral domain or is it a field? Let's take a look. So, 0 plus I, 1 plus I, 2 plus I, and 3 plus I are my elements. So down the side, I'm going to write the elements again in Z12 mod I. That'll be 0 plus I, 1 plus I, 2 plus I, and 3 plus I. Multiplying. Remember how we defined on how to multiply cosets. You multiply the elements and add a plus I. And of course, you have to be back inside the coset ring structure here, but no problems here with 0 plus I times 0 plus I. 0 times 0, yeah, pretty much is 0. And coset plus I. 0 times 1 is still 0 plus I. 0 times 2 is 0 plus I. So 0 plus I times 3 plus I is, yeah, what a surprise, 0 plus I. 1 plus I times 0 plus I is 1 plus I. Excuse me, 1 plus I times 0 plus I, yeah, give myself, that's 0 plus I. I was jumping ahead here. 1 plus I times 1 plus I is, 1 times 1 is 1. I can do basic math here. Plus I. 1 times 2 is 2 plus I. 1 times 3 is 3 to make it a coset plus I. 2 times 0, yep, still 0, plus I. 2 times 1 is 2 plus I, but here we go. 2 plus I times 2 plus I. Well, 2 times 2 is 4, but 4 is equivalent to 0. 0 plus I. 2 plus I times 3 plus I is 6 plus I, but 6, see, 4, 5, 6. 6 is equivalent to 2 plus I. And again, if you're seeing where I'm getting this from, remember how we did this before. You know, that 6 plus I is equivalent to 2 plus I because you're getting the same elements, but we call it this guy. You just don't write down the elements. I was just trying to show you what they are with this stuff. Okay, keep going. 3 plus I times 0 plus I, well, 3 times 0, yeah, pretty much is 0 plus I. 3 plus I times 1 plus I would be 3 plus I. 3 plus I times 2 plus I is 6 plus I, but 6 is equivalent to 2 plus I. And last but not least, 3 plus I times 3 plus I is, well, officially 9 plus I, but 9 is equivalent to 1 plus I. And again, if you don't know, there is a pattern for this thing. 9 plus I is equivalent to 5 plus I, which was equivalent to the 1 plus I. That's where I'm getting from. And also, I'm pretty much catching the pattern here. So, what kind of ring is it? Well, first off, we have an identity. 1 plus I is the identity because 1 plus I times any one of these elements gives me any one of those elements right back again. So we definitely have an identity here. But since 2 plus I times 2 plus I was equal to 0 plus I, that's called a zero divisor. We have a zero divisor. There's a big old 0 right in the middle of my multiplication table here. So I got a zero divisor, which means it cannot be an integral domain. So, but does the elements commute? Well, 2 plus I times 1 plus I is the same thing as 1 plus I times 2 plus I. So because your little diagonal here, they do have that symmetry look to it. So it does commute. So we do have commutativity here. So it commutes. We got an identity. So what kind of ring is it? It is a commutative ring with identity. But to be able to look at this guy to figure out what kind of ring it is, I actually had to draw out the multiplication tables of this guy. That's how you typically can tell what kind of ring it has. Well, that's not too bad if I only got like 4 elements, but what happens if it was like Z95 modded out by multiples of 5, you know, whatever, that could get rather large. So is there a better way? Oh, yeah, there's always section 6.3 about this stuff. But before we get there, we got some more stuff. The other thing I want you to focus on with this particular type of problem is this. Is the pattern unique, or have you seen this pattern before? I got 0 plus I, 1 plus I, 2 plus I, and 3 plus I. Those are my cosets in this ring of Z12 mod I. But if you look at these guys, man, they look awfully familiar. I've seen this ring structure before, and what that ring structure is actually equivalent to Z4 in this example. What was Z4? The elements were 0, 1, 2, and 3. And in Z4, you'll notice that 2 times 2 is 4, which is equivalent to 0. It has the same pattern. So when we have the same pattern with the addition, with the multiplication, just slightly different kind of way of adding and multiplying, we call that isomorphic. So we can create an isomorphism. And remember my definition of isomorphism, it's a one-to-one onto injective, surjective homomorphism mapping that takes one ring into another ring. So not only transfers the elements, it transfers how to add and how to multiply. But if you can create an isomorphism and get 2 rings that are isomorphic, they may look different, but they're actually the same thing. Great for code theory if you think about it, if you're trying to mimic something or other but hide stuff in patterns and like. So isomorphic means they're exactly the same thing. So even though this is an awesome new quotient ring, it's not really new. It's actually isomorphic to an old quotient ring we played with before. So isomorphic means, well, you created something new, but no, not really. It's actually something, it's just been repackaged. It's a new in terms of repackaging, but it's actually an old ring that you played with before. So those homomorphisms are going to be very important. So we're going to go back to homomorphisms. Now, I discussed this definition with you guys before. And so it was way back when in chapter 3 that I discussed it when we were focusing on subrings. And that was after we talked about homomorphisms, when we talked about subrings, I said there's a special kind of subring. And that subring was called the kernel of a homomorphism phi. So again, I'm going to define it. I know I've defined it before for you guys, but here it is one more time. Let phi go from ring R to ring S be a homomorphism of rings. That's my fancy term, so I can shorten up the English here. Let phi from R to S be a homomorphisms of rings. That means that phi is a homomorphism and R and S are actually rings. Then the kernel of phi, the kernel of your mapping, is a set K, which is equal to all the elements that come from R, which officially is your domain, that's what the little line here stands for, such that phi of those elements R actually equals the 0 element. These are real special when you look at mappings, especially when you look at stuff from high school and junior high school. When we looked at polynomials, we define polynomials over where they actually cross the x-axis, called the x-intercepts, roots, and zeros. This is the root in a 0, but it's in a higher plane of modern algebra, so we call it the kernel of the map. It's the focusing on the map phi, it's all the elements, the map over here to the 0 and S, where S is the range, the codomain, if you will, of where your elements are going from. So, theorem 6.10 says this. Let phi go from R to S be a homomorphism of rings. Again, that means that phi is a homomorphism, so we got all the definitions of homomorphism. R and S are rings. Then the kernel of phi is an ideal of the ring R. Let's prove it. We're going to prove it's an ideal. Now, if you look back at your last test and last homework sets and stuff, I believe you've proved it was a subring. But it's stronger than that. It's an ideal. So I'm going to redo the entire proof on this thing. So here we go. Here comes my proof. So always start in a direct proof with the givens. You were given that phi going from R to S is a homomorphism of rings. Thus, R and S are rings. Okay, and this implies, since they're rings, 0R will be an element of R, and 0S is an element of S. If they're rings, they got a 0 element. I will denote it, as I always do, that 0R is an element of R, and 0S is the element of S. Now watch how I pull some old theorems back on you. This is why you got to have all those theorems memorized, or at least at the ready, because I'm going to give them to you on a test that way. I'll quote the numbers because only I remember the numbers here. But after you've been through this class a few times, you'll remember the numbers too. So, since phi of 0R is equal to 0S by theorem, and it was way back when in chapter 3, Theorem 3.10, that was our favorite theorem with all the homomorphism mapping stuff that we talked about. Therefore, 0R is an element of K, and K is unempty. Now, let's talk about why this dude's in K. To be inside of K, way up here, this is the definition of what K is. So to be inside of K, you got to come from R. Well, clearly 0R comes from R because R is a ring. And you've got to have the property that phi of that element, in this case 0r, has got to be equal to 0s. Well, phi of 0r equals 0s by that theorem 3.10. Zeros always map to zeros under homomorphisms. So therefore, both things have been satisfied to be inside of K, so therefore 0R, because you have to come from R, 0R is an element of K, and K is non-empty. Remember, I'm trying to prove K is a ideal of R. So I'm going to quote Theorem 6.1. Theorem 6.1 says I got to have it to be non-empty, I got to have closure under subtraction, and then I got to have that special definition of ideal, where I'll have one element inside my set and another element inside the ideal, and then the product has to be back inside the ideal. So here, let's continue on then. So the next part of this guy is I got to show closure under subtraction. It's exactly the same thing as when we did subrings. So I got to give myself two elements. So my favorite two guys. Let x and y be an element of K. And you have to do this in order, because I've had a lot of students email me and ask me, why is the order important on the three parts you got to do on proving when we're doing subrings? I said, well, first you got to show it's non-empty before you can actually declare there's a couple elements in there. Because if you haven't proved it's non-empty, somebody's going to go back and go, wait a minute, you're letting somebody be in there, but what happens if nobody is in there? So there is a proper order of how we do these particular proofs. First, you show it's non-empty, so therefore there must be somebody there. Since somebody's there, well, let's just pick a couple arbitrary dudes that are there. Let x and y be an element of K. What does that mean? Then, x and y are elements of R. That's where you come from to be inside of K. And they have the property that phi of x must be equal to 0 in S, and phi of y has to be equal to 0 in S. That's what it means to be inside of a kernel of a homomorphism. Now, we have to set it up and make sure all things to be inside of K are satisfied. Well, as x and y are elements of R, then x minus y is an element of R. That first part about the subtraction has to be satisfied. Okay? And to be inside of, so to be inside of R. Now let's talk about phi. Also, phi of x minus phi of y is equal to phi of x minus y. This is one of your properties of homomorphism, but no. The property of a homomorphism is the plus. Phi of x plus y is equal to phi of x plus phi of y. But the minus actually came from Theorem 3.10 by Theorem 3.10. Thus, phi of x minus y would be equal to 0s minus 0s, which is equal to 0s by substitution. Since phi of x minus y is equal to phi of x minus phi of y, that's your Theorem 3.10. Go back and look at Theorem 3.10 if you've forgotten. And then phi of x, by definition of how we defined x and y, is equal to 0s, and phi of y equals 0s. So I get to replace phi of x minus phi of y with 0s minus 0s, which by definition is equal to 0s, and I just call that by substitution. Hence, x minus y is an element of K. Now again, I'm going to underline this for you guys just to show you why is this guy, what has been satisfied here. To be inside of K, this is the set K that I've defined up here, the kernel of a homomorphism. You've got to come from R, and phi of u must be equal to 0. And we're focused on x minus y, show that the difference is inside of K. So x minus y had to come from R, that has been clearly stated there, and phi of x minus y does equal 0 in S. So the two properties, where I come from and what property I have been satisfied with the x minus y. That's what puts x minus y inside of K. Now the third part, I got to pick one of these elements. So as, pick my favorite guy, x, is an element of K, then, state what that means, x is an element of R, and phi of x is equal to 0 in S. where I come from and what property I have since I'm in K. Go ahead and state that. But now I need an arbitrary element in my ring. And we're trying to show that K is an ideal of ring R. So K is going to be an ideal of R, so I need an arbitrary element in ring R. So, what's more arbitrary than little r? So let little r be an element of big R. But let's see where he goes. Remember, we got a mapping. So, since he's arbitrary, therefore, there exists a little s element of big S such that phi of little r will be equal to little s. Remember, phi is a homomorphism. It takes elements from ring R to ring S. So if you're an element of ring R, you're going to eventually, if you apply phi to you, you're going to be mapping yourself over to ring S. So I'm going to let little s be an element of big S such that phi of R equals S. Now let's talk about the product. Well, as x and little r are elements of R, this is my focus because I'm trying to show the elements, again, focus on being in K, and I'm talking about the multiplication. So the product of my two elements from R have to be in R. So as x and r are elements of R, then x times r is an element of R because R is a ring. That's all I told you about R. It was just a ring, but closure under multiplication satisfies. Also, now let's talk about the property, the phi of it. Let's see where that goes. Also, phi of x times r would be equal to phi of x times phi of r. Now, why is that? That's not any fancy theorem. That is straight up by definition of homomorphisms. Addition and multiplication. Phi of x plus r is equal to phi of x plus phi of r, and phi of x times r is equal to phi of x times phi of r. That's the definition of being a homomorphism. Okay? Thus, phi of x times r is equal to, well, phi of x is equal to 0 and s, times phi of r, that's very arbitrary, that's just equal to s. So phi of x times r equals 0s times s by substitution. Hence, phi of x times r is equal to 0 and s. 0 and s times any element of s is equal to 0 and s, and you really don't have to state the proper reason for that. It's property of 0 if you want to really put it in there. But 0s times s is pretty much equal to 0s. You can just put equal to 0s by substitution and be done with that. Okay, therefore, x times r is an element of K. Again, I want to highlight this because these are the things I look for and you should look for when you're doing these proofs, especially under the homomorphisms. So here we go. To be inside of R, you had to come from, to be inside of K, you had to come from R. So x times R is an R. There it is. I'll underline it so you guys can see it. There it is. And the other property is that phi of x times r equals 0 and s. Well, I restated it over here. So phi of x times r equals 0s. So where I come from and what property I have been satisfied for K. So x times r is element of K. Question for you. Did I give you a commutative ring for R? No, I did not. So I'm afraid you've got to have another paragraph. You've got to state it, but it's going to follow directly. If I do not give you a commutative ring, you've got to show it the other way as well. And so I'll pick, instead of word as, pick the new paragraph since x and r are elements of R, because the givens are the same. So you pick it up right here, we start to maneuver them. So since x and r are elements of R, then r times x, the other way of multiplying these two elements, x times r is an element of R, again, because R is a ring. Also, phi of, just make sure you get the right order, r times x would be equal to phi of r times phi of x by definition of homomorphism. Thus, I'm using the same words. Why? Because I'm math. Why do I want to change my words that were perfect to begin with? Thus, phi of right order, r times x would be equal to s, but right order, times 0 in s, which is equal to 0 in s. I'll write it this way this time, by substitution. Hence, phi of, excuse me, actually I got that one. So hence, r times x, we'll put it right there. R times x is an element of k. Again, I want to underline what the important parts are to be inside of k. R times x is an r, and phi of r times x equals 0 in s. Hence, r times x is an element of k. And then I got just enough room to put the famous concluding statement. Therefore, by theorem, your new favorite number, 6.1, k is an ideal of R, because that's where the elements came from. And I'm done. So here is your very elaborate proof. And the other thing that I'm sure you're noticing about my awesome videos is we're in chapter 6 now. The proofs, when I started out, were about yay long. But by the time you got to chapter 3, they were about yay long. Well, now we're in chapter 6, so they fill up a whole page, and I'm writing it. I don't have, font 45 handwriting either, so I'm writing this. It's not small, but it's not overly small, but most important, it's not overly large. If I did overly large handwriting, I could be there for days with pages and pages of this stuff. So you have to have a neat but relatively good font type of handwriting to be able to get this thing all on one page, because that's all I give you guys on the test and the homework sets and stuff. So there you go. So this is a great proof, and also notice the details of the proof and stuff. So can we make them even harder? Sure we can. Let's take a look at this guy here. Here's another theorem, and this one I'm trying to help you guys out with future homework problems that you'll notice that have already been posted for you guys. So here is a theorem, and I didn't put a number on it because it actually comes from homework stuff. I just recreated and changed all the letters for it and stuff like that. So here's my theorem. Let phi go from R to S be a homomorphism of rings, and let W be an ideal of S. So I'm giving you W is an ideal of S. Then L, which is equal to the elements P from R, such that Q is equal to phi of P for some Q in W, is an ideal of R. As I mentioned to you guys before, way back when in chapter 3, when we were talking about homomorphisms, the beauty of homomorphisms is that they are property preserving. So if I've got phi taking the set ring R into ring S, and phi maps that sucker over from ring R to ring S, what's going on here is this. If I've got W, here's W, inside of ring S, and this guy is an ideal. Very similar to what we did before last time we talked about being a subring. Now, he's an ideal. The dudes over here, which I called L, over here inside of ring R, that actually map to the W's, since this W is an ideal of S, that's given, what we're going to prove is L is an ideal of R. Ideals map to ideals. Whether you start with an ideal, where you end up is going to be an ideal. if you guys got some stuff mapping over here and where they're ending up is an ideal of S, the guys that map to them will form an ideal of R. In homomorphisms, it's property preserving. We proved even that on terms of your homework sets and questions on test. You know, zero divisors map to zero divisors. Subrings map to subrings. Ideals will map to ideals, okay? So this one's going to be a little bit longer proof, so I'm going to kind of stretch it out this way a little bit here. So let us prove this thing. So I'm going to prove some dude is an ideal. I'm going to quote my theorem 6.1. So here we go. Start with your givens. Given phi going from R to S is a homomorphism of rings. Thus, R and S are rings. Also given, this is some kind of special, also given W is an ideal of ring S. I'm giving you W as an ideal of ring S. Okay? Well, here we go. Since R and S are rings, then 0R is an element of R, and 0S is an element of S. Also, as W is an ideal of S, that also means he's a subring with an extra property, then 0S is an element of W. I'm going to be very specific of where I'm using W as an ideal of S. Keep that in mind when I do this. So here we go. By theorem, my favorite number there, 3.10, phi of 0R is equal to 0S. Zeros always map to zeros. And 0S is inside of W, therefore 0R will be an element of L, and L is non-empty. Now I want you to pay attention to this particular proof because you've got a lot of details on this thing and it's very easy to get lost. So let me underline why L is non-empty. To be inside of L, where do you come from? 0R came from R. First you focus on where you come from. Then what property do you have? Then phi of that element, phi of P will have to be equal to Q for some Q in W. Well, phi of 0R equals 0S, so that equation of the homomorphism is satisfied, where 0S came from W. So with this one, I got where do I come from is one, and then I got two properties about what properties I own. So 0R is an R, and I've got 0S being element W, and phi of 0R equals 0S. So I'm mapping 0R to an element of W. All things have been satisfied. That's what puts 0R inside of L, and L is non-empty. I'll continue to do this as I go through this proof. Now, continuing on. Now I need to show closure under subtraction. So I got to give myself two elements. You know it. Let my favorite two guys, X and Y, be an element of this time it is set L. So I just give myself, now that I prove it's non-empty, I'm allowed to grab myself a couple of dudes, X and Y. Let X and Y be an element of L. What does that mean? Therefore, where do you come from? X and Y are elements of R, and this property has been satisfied. So this is a great time. If you look at just definition, so I'm trying to help you guys out with the structure of this stuff. You can call these elements that you start with anything you want to. But you notice this guy is also equal to this guy, but then they also introduce a new element. When they introduce a new element inside your set notation, is a great time for subscripts. So I can keep up with it, I'm going to call the dude that my x and y are equal to will be called q's. And of course I need two of them, so I'm going to call, and there exists, I'm going to call them q1 and q2. Where did these q's come from? W. Elements of W, such that phi of x will be equal to the first dude, q1, and phi of y will be equal to the second dude, q2. Okay? So, that right there is where most students will mess this stuff up. They will get lost in terms of what does it mean to be inside of L. So I read it. I create myself two guys. Where do I come from? R. What property do I have? Phi of that same element, I'm calling x and y, has got to be equal to a new element, that's the subscript thing, where that new element came from W. The Q1 and Q2 came from W, where I have my equations. Now let's talk about subtraction. Well, since, catch a pattern on this, x and y are elements of R, then x minus y is an element of R because R is a ring. Okay? Also, so we got that part, x minus y is an R. Now let's talk about the phi element of it. Also, put it over here if you guys can see it. Phi of x minus y, that's going to be equal to phi of x minus phi of y. And I want to remind you, why is that? That is not the definition of homomorphism. Homomorphisms, the definition deals with pluses and times. This is subtraction. That was a special theorem by Theorem 3.10. Thus, phi of x minus y is equal to q1 minus q2 by substitution. Okay? Hence, as q1 and q2 are elements of W, then q1 minus q2 is an element of W because W is an ideal of ring S. We're focusing on being inside of W, which is an ideal S. W is a subring with extra properties, so it also has closure. Hence, x minus y is an element of L. Again, I want to underline this for your benefit, so when you actually do proofs like this, you know what you're looking for. To be inside L, you had to come from R. X minus y has got to come from R. That was stated here. Okay. 2. Phi of x minus y has got to be equal to some dude that came from W. Phi of x minus y is equal to, my some dude in this case is q1 minus q2, where that q1 minus q2 is from W. Where I come from and what properties, there's two of them, I have been satisfied. That's what puts x minus y is an element of W. Well, 2 down, 1 to go. Now we got to talk about arbitrary elements inside of my set and the like times an element inside of my ideal that I'm trying to prove. So I had to use one of my elements. Well, typically with the x and y, I'm going to start with the x. And I've already stated them, so I start with a new word, as, and just reclaim it. X is an element of R, then, excuse me, x is an element of L, then x is an element of R, and there exists a Q1 element of W such that phi of x was equal to Q1. I'm literally just restating what I did up here with just one element. Now the other element needs to be arbitrary. Now, we're trying to show that L is an ideal of R. So I want to start with an arbitrary element of R. So I do that by obvious reasons. I'm going to let little r be an element of big R. Very arbitrary, doesn't even have a subscript on that sucker. All right. So let little r be an element of big R. Then there exists, because we're doing mappings here, an S element of big S such that phi of little r is equal to little s. Now this is very basic of ring homomorphism. R's map to s's. There's a little r in big R, there exists a little s in big S, such that we have a map phi of r equals s. That's the whole idea. You map from R to S. Now, continue on. Let's talk about the products. Well, as X and R are elements of R, X is an R and R is an R. X and little r is an element of big R, then X times R is an element of R because R is a ring, basic ring, closure property. And as phi of X times R, same element, is equal to, let's see who that's equal to. Well, that's the homomorphism. Phi of X times phi of R by definition of homomorphism. Then phi of X times R is equal to, now phi of X was equal to Q1. Phi of R mapped to S. So that's equal to Q1 times S by substitution. Okay? But here it comes. Always pay attention to where elements are. Since Q1 is an element of W and S, little s, is an element of big S, and W is an ideal of S, then Q1 times S is an element of W. That's a property of ideals. I'm being very specific of where I'm using W as an ideal. So, therefore, X times R is an element of L. Again, I want to underline the importance of, I go back to that structure of L. To be from L, you've got to come from R. X times R came from R. There she is right there, statement and reasoning. Also, to be an inside L, you've got the property that phi of X times R equals some dude. Phi of X times R is equal to, in this case, the sum dude is the Q1 times S, where that somebody is in W, where the Q1 times S is an element of W. So again, where I come from and what property I have been satisfied. That's what puts X times R in L. Did I give you R or S or anybody? Did I give you anybody? Was it a commutative ring? Of course not. So as, and I pick it up here, okay, the part S, I don't need to restate where the elements came from. It's when I start maneuvering them. And I start maneuvering them as I pick up the elements and talk about where they've come from. Well, so as R and X are elements of R, then R times X is an element of R because R is a ring. And as phi of R times X is equal to phi of R times phi of X by definition of homomorphism. Homomorphism. Okay. Then phi of r times x is equal to s times q1 by substitution. And since q1 is an element of w and a little s is an element of big S, then, let's rephrase that, and w is an ideal of S, then S times Q1 is an element of W. Therefore, R times X is an element of L. Now, what I really wanted to show you here was this. Starting here at that word as, I recopied the exact same thing except putting the elements in reverse because I was not given anybody being a commutative ring. So therefore, use that structure. So getting it the paragraph down first and then kind of reusing it as you go along, it kind of builds on that idea. One last statement to declare victory. Therefore, by your favorite theorem, by Theorem 6.1, L is an ideal of R. Remember where the elements came from, R, and that's what I was supposed to be proving. Now, so here is an awesome proof of that particular theorem, and yes, it does fill up the entire page. I could have stretched it out a little bit over here on either side and made it a little bit more neat and centered, but you get the idea that these proofs, especially under the homomorphisms, well, they tend to be rather long. I'll give you that, but that's all right. You're in chapter 6 now. Get used to it. So, here's the other thing. I gave you a problem on your homework, which is very similar to this, except I reversed it. So things are a little different. I changed the letters, of course, too. But in the problem I gave you in terms of the homework, I gave you phis or ring homomorphism, but this time I gave you that somebody is an ideal of ring R, and then you had to prove that the set W, or whatever letter I called it, was an ideal of set S. But the subtle difference on this one was I had to give you not just any homomorphisms, I had to give you a surjective homomorphism. And let me explain why. Because without the surjective homomorphism, these parts, well, the zeros will be the exact same. These guys will be pretty much the exact same, except when you start out with your elements in whatever letter I give you, they come from S, but to actually get them over there in terms of R, because you have a surjective homomorphism, anybody over here in S, there's going to be somebody to map to it. You don't have to worry about, well, I picked an element over here, whether it be in W or inside of S, that nobody maps to. Well, if you play around in the S world, if you don't have a surjective homomorphism, you could be poor pickers and actually pick some poor sap over here in S that's very lonely and nobody mapped to. Phi maps R into S, not onto until I give you surjective homomorphism. So, you will actually use the fact that there's a surjective homomorphism, so whenever you pick an element over here, and whether it be in S or in W, you're guaranteed there's going to exist an element in R or in L that will map to them based on the definitions. And that's very important, especially when it comes down here where you need your arbitrary elements. So if I start picking an element little s, element of big S, there's going to exist a little r inside a big R because phi is a surjective homomorphism such that, phi of R equals S. You've got to have a surjective homomorphism when you arbitrarily pick elements in S and you want somebody to map to them. So that's the subtle difference, but the structure is going to be very similar. So this is why I'm trying to help you guys out with the class. Now, most people, when I teach class regularly, have to write this stuff and keep up with me. Now I'm doing it on video because I'm ordered to do so. You have the ability to pause the thing, so knock yourself out. But this is a great proof, something well worth studying to get you prepared for your test number 3 as we keep cruising. Let's continue on. So there's some more major theorems from section 6.2. 6.2 is kind of a big section here. And 6.3 is a little bit shorter. It's more of ideal structure stuff here. But here we go. Continuing on in section 6.2. Theorem 6.11 says this. Let phi go from R to S be ring homomorphism. Homomorphisms of rings. Okay? With the kernel K. So the kernel, remember, is all the elements in R that map to the 0 element in S. But here's the deal. Then, if K is only equal to one element, the 0 element, 0 in R, if the kernel only has a 0 element R, remember, zeros have to map to zeros, so we know that phi of 0R equals 0S. But if that is the only element that maps to 0S, then, if and only if, phi is injective. Injective means 1 to 1. So here's another wonderful theorem. If I ever want to prove that you have an injective homomorphism, I mean, there's the definition. I can show that phi of A equals phi of B, and I have to show that A equals B. That's one way I can do it. But another way we could actually do it is by, if you look at the kernel of the homomorphism, all the elements from R that map to S, and if there's only one element, 0R maps to 0S, then automatically phi is going to be injective. And goes the other way. If phi is injective, automatically 0R will have to map to 0S, and that's the only dude that maps to 0S. And we've used that concept in that direction before. But going the other way, we put it as a theorem 6.11. So if the only element inside your kernel, the only element that maps, that goes from 0R into 0S, goes from R into 0S, is the 0 in R element. Only phi of 0R maps to 0S, then phi is going to be injective, and it is both ways. Another theorem that kind of sets you up with some of the major isomorphism theorems is this. Let I be an ideal in a ring R. Then the map pi, going back to these Greek letters again, pi mapping R to the R mod I. Remember, this is a quotient ring when I is an ideal. So I is an ideal of ring R. So R mod I is going to be a quotient ring, so it's a ring. So phi is going to be a homomorphic mapping here, given by phi of R is equal to R plus I, kind of what we call the natural mapping. I'll talk about that in a second. So how do I go from a ring R to a quotient ring? Remember, quotient rings are the cosets, A plus I. We'll just map them. R maps to R plus I. That's what we're saying here. For any R in R is a surjective homomorphism with the kernel being I. The kernel of pi, that is equal to I. So all the elements that actually map to the 0 element over here, this would be 0 plus I, is actually I itself. So when you, with this natural homomorphism, it's a surjective homomorphism. Everybody over here is going to get mapped to, surjective onto, and the guys that map to the 0 element will actually be, so the kernel of pi will actually be all the elements from the ideal I in R. So this is just a definition, and this definition, well, first off, it's a theorem about the idea of this natural homomorphism going from R into R mod I, and by this particular description, pi of R is equal to R plus I. It's going to be, here's the theorem, it's a surjective homomorphism, and the kernel of pi is actually I. And again, down below it's where I'm coming with that definition thing here. The map, pi, going from R to R mod I, by this map, pi of R equals R plus I, making that's the coset there, is called the natural homomorphism. It's so useful, it has a name. So, what's the big deal about this? Well, this theorem, with the kernel being I, and the definition of this particular map being called the natural homomorphism, sets us up with what we call the first isomorphism theorem. And will we do a lot with it? No, but let me explain what the big deal is. All right, so this is called, and you're in trouble when they start naming theorems here, the first isomorphism theorem. So let phi go from ring R to ring S be a surjective homomorphism of rings. So it's surjective, so it's going to be onto. So everything over here in S is going to be covered here. So phi is going to be a standard homomorphism from ring R to ring S, which is a surjective homomorphism of rings. And the kernel, we're going to call it K. So this is, the kernel is literally all the elements in ring R that map to the zero element S. Then the quotient ring, R mod K, because you know kernel, we just proved it, is an ideal of R. So the quotient ring, R mod K, is isomorphic to S. So let me show you the picture. This is what they don't put in the book for you guys. So here's my picture. So this is what I'm trying to describe to you guys. Phi is going to be a homomorphism. You're going from ring R to ring S. Now it's surjective, so everybody over here in S is going to get covered. So phi is a surjective ring homomorphism from ring R to ring S. The natural homomorphism, pi, takes R into R mod K, where K was the kernel of phi. But K, the kernel of phi is a set of elements, which is an ideal, so you can mod out by it. And this is actually a quotient ring. So it's a ring, we call it a quotient ring, but so pi will just take R into R mod K, where K was the kernel of the original phi map. Then you automatically get that R mod K, this quotient ring, is actually going to be isomorphic. That means not only is it injective, it's surjective. Surjective, because everybody over here in S is being covered, but it's injective, 1 to 1. You can create a 1-to-1 onto map. Oh, geez, Dr. Taylor, that's great. What does that mean? No, it means this. Why do we study this stuff? Well, number one, the proof aspect and the structure is beautiful. But where do we really use this stuff today? And why do people in the NSA want me to help them out? And that was one of my first job applications that they wanted me to get hired from, was the National Security Agency. And this is one of the reasons for that. Let me explain. Code theory. What's code theory here? All right. S is basically our alphabet with maybe some symbols and the digits 0 through 9. This is pretty much how we code everything in English. 26 letters and 0 through 9, 10 digits. And I can throw some little symbolisms and stuff like that in there if I need to, But pretty much, that's pretty much 36 plus elements that I need to cover, but I need to code this stuff. Now, R is going to be my code. But not only do I want 36 elements, I want to throw some stuff in there that is red herrings, that is stuff that really is not coded at all. It's just there to people that are trying to break the system. They're going to try to follow these elements that I'm going to create, which actually go nowhere. I want them to kind of follow these things so they can't break my code. So I'm going to add a lot of these elements. So the elements that I'm going to add to R, I'm going to put under the kernel of phi. I'm going to map them to the 0 element, to nobody. So when I map those guys to nobody, okay, but there's a lot of them. I could put hundreds of thousands of those elements in there, but they don't really map to anybody because I just got to cover my stuff that needs to be coded, my 26 letters and my 10 digits and any other thing that I want coded with that. But you can add on to the list, but let's just focus on the classic 36, A through Z and 0 through 9. So I've got this going on. I add a bunch more elements into ring R to create a ring with under the addition and the multiplication. But when I mod out by all those red herring elements that map to 0, okay, that actually creates the isomorphism from the code to the actual letters that I want to do. So isomorphism goes forwards and backwards. It's 1-to-1 onto map. So I can go from here to the code and code back to here. This is what the code's going to be in. So this is that direct substitution code, as it's called historically. So element gets coded and code goes right back to the element. But the kernel are all the extra elements that I'm trying to throw off everybody else at. This is the idea behind, not just NSA and what our military does in terms of coding some of the things to our military and stuff, but we live in the 21st century. People aren't just after our military secrets, they're after my credit card and my bank account numbers and all the other things that I have to have coded this day and age, especially with the modern day of computers. This is setting up with that idea of security systems and stuff, and it's going through the idea of homomorphisms and how to hide stuff. That's what's going on, and that's what makes the, quote, first isomorphism theorem very important. So you get to see the ideas, especially with the elements that you kind of don't really want them to go anywhere. You're going to make sure they map to the dummy 0 element over here, and then the rest of the elements will map to where they need to go. So this is a kind of an important concept here, especially for my computer science majors that are into cybersecurity and the like. So there you go. So this is the end of section 6.2, which means there's only one more section to go through, which is section 6.3, which is going to kind of tie a lot of these things together and talk about the different types of ideals. And mainly we're going to focus on two of them, prime ideals and maximal ideals. But that'll be on section 6.3.